So last time we talked about Stokes theorem and divergence theorem. This is a summary. So whenever you see the formula, it's an abbreviation of the statement. So the Stokes theorem says that if you have a vector field and oriented curve which bounds a surface in three-dimensional space, you can retrieve the work done along the boundary of that curve by taking a surface integral of the curl over the surface. And this is the Stokes theorem. I think Stokes. And then the divergence theorem tells you that if you have a surface which is bounded, a closed surface, so the circle around this single S means that C is closed, and often we put a circle around this double S in order to say that S is closed, meaning that there's no unbounded region, and there S is surrounding entire some three-dimensional volume. And if you want to find the flux from that surface, this is equals to the volume integration or triple integration over the volume that's surrounded by S of divergence of the vector field. So usually, since we have to put dx, dy, dz, sometimes we put dv, meaning that it's a volume integration. So this is called the divergence theorem. The divergence, of course, is not a name of person. So again, let me say that it's very important to know that which orientation we're taking these integrals. So only the last one is the thing that we don't need an orientation. This is simple triple integration. All the other thing requires orientation. So whenever you take the vector field, line integration of a vector field, you need the orientation of a curve. And the curl of a vector field is also a vector field. Okay? So we need orientation of surface S. And here we're talking about the flux. So there is a flux, outward flux and inward flux. You have to figure out in which direction you're talking about. And the relation between these orientations are the following. So whenever you have a curve that bounds the surface in three-dimensional space, you want to apply your right-hand rule. In other words, you want to put your head up to the upward direction, the orientation of a surface, and while you're moving along this orientation of a curve, your left arm should be inside of the curve. So in this case, this is the orientation of a surface S according to the orientation of a boundary curve C. And if you want to talk about the divergence theorem, then you have to talk about the volume orientation of a surface that bounds the volume. If you want to talk about the volume inside of this surface, then your orientation of surface is the outward direction. So this is the orientation, and this is the volume, and S is the boundary of that volume. Okay? So remember this picture and remember that formula. So once everything should be clear, and we also talked about the intuitive proof for the Stokes theorem. Basically, the rigorous proof is the same. So we're going to show some rigorous proof. Did we? I think we didn't. Okay, so I think we didn't show the rigorous proof yet. Okay. Let's give a proof of Stokes theorem. So what we're going to do is assume a very special kind of situation, which is S is given by a graph of function And this graph of function is defined on the xy plane, a domain on the xy plane, which satisfies that a is from a to b and y is from g1x to g2x. So if I have to draw this, then this is how it looks like. So we have a graph of two variable function as a surface, and if you take a projection onto the xy plane, there is a projection of this surface on xy plane. This is y and this is x. So here is z-axis, and I will call this as d, and I can okay, so maybe I have to draw it a little bit differently. So I will just make it as convex shape. So I'm going to take the range of x from a to b. Then I'm assuming that my y range from g1 to g2 according to the point of x. So this is g1 and this is g2. So these g1, g2 are a function of x because it gives the minimum and maximum of y in order to have a point lies inside of d according to the point x. And let's try to find out the left-hand side and right-hand side of this integration. So let's try to compute this. So what do we get? What do we have to do to find out the line integral? Well, let's say I want to give a name for the vector field. I want to give a name for the coordinate for the vector field. I'm going to say this is PQR. Okay. So let's try to calculate. So first of all, I have to parameterize these curves. This is curve C. And also I'm going to give my orientation as counterclockwise, meaning that if I project that orientation to the xy plane, this curve, projected curve, will move along this projected curve by counterclockwise direction. So let's parameterize CT as the following. So first of all, there's no way I can parameterize in single function because the lower part is parameterized by G1 and the upper part is parameterized by G2. So let's say I'm going to parameterize in two curves, which one is C1 and C2. Well, let's say C1 bar and C2 bar. So that will corresponds to C1 and C2 here. Okay, so C1, C2 are the three-dimensional curve. C1 bar, C2 bar is the projected curve. So let's talk about C1T. So when I do that, this is, I'm going to parameterize by x, but I'm not going to, well, maybe I've just used x as a parameter instead of t because I'm going to change it to x anyway. So x coordinate is x, and y coordinate is G1. And what's the z coordinate? Z coordinate follows this function. So I plug in x and y to the function f. So this is f x comma g1x. Okay. So this is c1x and c1x, yes. And c2x is x g2x comma fx g2x. Okay. One more parenthesis. So I'm going to split this line integration into two pieces, C1 and C2. So when I integrate over C1, my range of x is from A to B, because I want to go counterclockwise. Okay, A to B. And let's say P, Q, R, that's F, and inner product with C prime T, C prime X in this case. So C prime, more specifically, it's C1 prime. So it's 1 G1 prime x and what? So look carefully about the last coordinate function. So this is single variable function, but it's a composition of multivariable functions. One is f, and the other is these parameterization of x and y coordinate. So when I take a derivative of x, I need to use the chain rule for the multivariable function. So when you use the chain rule, let's say f of x. So first I take the partial derivative of this function f with the variable, first variable x, and then take the derivative of x again. So it could be confusing because I used x for the first coordinate variable for the function f, but this f, this x and this x is not the same thing. But anyway, I will use the same notation here. So take the partial derivative, and derivative of x by x is 1, and add with the derivative of fy times the derivative of inside the function y. So this is y, and if I take the derivative, I get g1 prime x. Okay, so this is c1 prime. Okay, and dx. Right? And then I have to add one more thing. Add with C2 line integration. So whenever you think about C2, now I have to go this counterclockwise direction. So x's range from B to A, okay, instead of A to B. And PQ are the same. And what? I have to take the inner product with C2 prime, 1 G2 prime, and fx plus fy G2 prime x. Okay. So remember that even though I use this fx, this is not a constant. So this is a two variable function with x coordinate x and y coordinate g1x. Okay. So everything is in terms of x and dx. And let's combine these two, taking same limit from a to b. Then I have to take a minus sign here. So this becomes a to b of, let's take inner product everywhere. So first of all, I have P there, right? I have P there, but that P is when I use these coordinates here. So x, g1x, and it's going to be long expression, but I'll do it anyway. So that's come from the first integration. And the second integration also contains P, but this is not the same P in the first integration because this P is coordinated by C to x. So I have to plug in x, g to x, and f to P. So P, x, g to x, and fx, g to x. Okay. One more parenthesis. And the same thing for Q. Instead of instead of 1, we have g1 prime multiplied, but the coordinates are the same. So we have x, g1x, and fx, g1x times g1 prime x minus, same thing here, q x, g2x, fx, g2x times g2 prime x, okay? And then what? The last one, do we have r, x, g1x, and f, x g1x, and then I multiply the whole thing here. So now I'm going to, let's plug in the xy coordinates here. So fx at x g1x, because if I'm not specifying the xy variables, then it's going to be confusing with the fx in here. And then plus fy x g1x times g1 prime x. So that's the first r. And the second r is from here, x g2x and f x g2x, and multiply with fx. Now I have to plug in c2 coordinates for fx here. So x g2x plus fy x g2x and what times g2 prime. Okay, parenthesis, and then end of integration dx. Okay, so that's a line integration. If you really want to do the line integration in this specific form, just plug in xy, f or g1, g2 with the appropriate formula. So that's how we get the line integration. Let's talk about the second part of this Stokes theorem, the right-hand side of the Stokes theorem. So right. Let's talk about it. Okay, so now when you want to do the line surface integration, you need to find out the normal direction of this surface. So let's call it n here. So so in this picture, I gave the orientation of curve, boundary curve as counterclockwise direction. So this should be my normal direction to the surface. And this normal direction could be achieved by taking a cross product of parameterization of the surface. So the way we parameterize the surface is, since S is a function, graph of a function, two-variable function, I can give a map from the domain D, the two-dimensional domain D, to xy, fxy as a parameterization of the surface. So if I take Sx, so taking a partial derivative, so meaning that I'm only changing the x coordinates, then my curve on the surface will move downward to this direction, right? And if I move my y coordinates to the parameterization, I might move this direction. So basically, it means that if I take partial derivative by x, I get this direction, and partial derivative of y gives this direction. So in order to have the n direction, I need to take the cross product in the order of Sx and Sy. So my n is Sx cross product Sy divided by the norm of this cross product. But remember how we derive the formula for the surface integral. In fact, we don't need to actually use this, because what happens is, if we start thinking about the change of variable, or in other words, integration by substitution, then this line surface integral over S becomes the double integral over the domain of parameterization, and then that becomes the vector field inner product with Sx, Sy, dx, dy. If you're not remember correctly, then just look at the previous lecture note. And what is x? What is Sx? So just simply take the partial derivative in x. So we get 1, 0, fx, and sy is 0, 1, fy. So if I take the cross product, Sx, Sy, then that becomes minus fx minus fy, 1. That's the cross product. And let's multiply together. Again, before let's take one more step together. So when you do the integration over d, I can make my double integration as an iterative integration by Fubini theorem using this description of d, where x is ranging from b, y is ranging from g1 to g2. So when x is ranged from a to b, y range from g1 to g2. So that's a double integration in iterated form. And let's plug in here. So I don't remember the formula for curl. So what's the first coordinate for the curl of f? Do you have any note? What's the curl of f? So what's the first coordinate? Please say aloud. Just look at the notes. If you have a note. Q sub z, okay. And RZ P what? Py? Px? No, it doesn't make sense. What's the second coordinate? Pz minus Rx. Right? Okay. Yeah, Qx minus Py. And then minus fx minus fy 1 dx dy. Now let's try to make it simpler. All right, these are the same. So minus ry fx plus qz fx minus pz fx is it minus? Oh, I forgot. No. Okay, well, fy, sorry. Fy plus rx fy and qx minus py dx dy. Okay. So everything is in xy coordinates. Okay, so these are two variable functions. Now I want to make integrate fundamental theorem of calculus. So which means that I want to integrate over. I'm sorry. So I forgot to put the order. So we have integration over y first, and then x. So dy dx. Okay. So maybe I can cheat a little bit because eventually I want to make the integration. If I did the inside integration once, I want to make everything like in this form. So how I want to cheat is I want to find out some del del y formation when I plug in y from g1 to g2. I want to get these fp minus p here. Okay, so let's find out which term can be written as that. So we have same integration. Let's talk about py. Well, there's obvious one here, right? So py here, right? So this is something that I get when I integrate a partially take a derivative over y. Then I also try to get integration over y. So basically, I get the p itself again, okay, by fundamental theorem of calculus. If you're just looking at py, integrating over dy, then you get p, right? So a to b of, let me write it again, g1 x, g2 x of minus py dy is very special because I will get p. So let's leave it here. And also, let's cheat a little bit more. I want to get a q something, g1 prime, g2 prime there, by taking integration over here. Let's see. So I have q x here. So q is here, right? So I have to combine that together. So how should I combine them? So let's, since in my head it's confusing, so let me first clearly set that these functions are function on xy coordinates, okay? Two variable function. But think about original vector field. This vector field f is consists of PQR coordinate function, and these PQR coordinate functions are three variable functions, okay? So where does last coordinate disappear? It's not disappear. It's just that we automatically have z coordinates fixed by fixing xy coordinates. Z is fxy. So whenever I wrote this, what happens is, for example, qz fx is actually qzxy fxy times fxxy. Okay, that's what really happens. And also this qx. Oh, by the way, so all right, maybe I should be careful about this one too, because I forgot. No, yeah, I forgot to put. I forgot to mention this last ones here. So maybe I take back everything. So just be cautious. All right, so yeah, so this is what really happens. And let's go back to original case here. So let's see. So I want to have this. That means pxg1x fxg1x minus, so minus pxg2x fxg2x here, parenthesis again, here, is equals to pxy fxy, and y plug in y from G2, sorry, G1, G2 here, right? As if I'm taking single variable integration. So maybe this is an antiderivative of some integrand, and then I try to make a fundamental theorem of calculus. Then I want this to be the result after I take the single variable integration. And what we want is this. And I want this as an antiderivative of something inside by integrating over of y. So here. So let's see. I really have to be careful about this. So when I take the partial derivative of y of this kind of function, so this is what I want as an antiderivative, but as an inside of an integration, the partial derivative of y of this function should be inside of this integrand. So let's take a partial derivative of that function, p xy fxy. Okay. So then, by the chain rule, I have to take the partial derivative of each partial derivative of p and then multiply with the partial derivative inside. So first of all, if I take a partial derivative of x, then I take the multiplication with integration derivative of x by y, which is 0. Okay. If I take the partial derivative of y, then I have to take a multiplication with y divided by y, so it's 1. And then we have a partial derivative of z, and then we multiply that with f prime y, fy, fy. Yeah. So this is the result of partial derivative. So remember that pz is a partial derivative of p by z because p was originally a 3-variable functions. Okay, so when we use the chain rule, we have to use the nature of these multivariable functions. But anyway, so in order to have that, I need px plus pz times fy as an integrand. Okay, so that I was partially right, but I'm not just need that. I also need this and this. Okay. So let's make one by one, step by step here. So let's combine these two, G1 to G2, and let's say I take a minus outside here, and py, why is it py? Oh, sorry, this is py, my mistake. This is py, sorry. So py plus pz fy. So that's the integrand. Is the partial derivative of these two variable functions. Okay. Therefore, I can use the fundamental theorem of calculus to say that this, if I take the original function here as an antiderivative, is equals to a to b of p x y fxy from where? G1 to G2, right? But I have a minus. I can put that minus to interchange this G1 and G2. So I can make a plus, and my limit will be G2 to G1, which is exactly the same here, and dx. And that makes what? So since if I do this, then I get this, and that is appear here. Okay? So I have matched these two terms with the first term here. And then maybe I can erase this. I don't want to erase that. Let's talk about the second part. The second part of the left side, this whole thing is the left side of the Stokes theorem, says that Qx G1x fx G1x minus Qx G2x fx G2x 1, 2, 3. And you see that this is actually equals to what we can express as plug in y from G2 to G1 for this kind of two-variable function only for y. Okay, so I want to find out how I get this as an antiderivative in terms of y in the integration. So let's think about I have to go backward. I want this to be antiderivative. And in order to find original function, I take the partial derivative of this function, right? So take the partial derivative of Qxy fxy. So then I have Qy plus Qz fy, right? That's it. So this is the antiderivative, and we have this Q. Oh, okay. So I forgot about this one. Sorry, I had this G1 prime and G2 prime, right? Sorry about that. Sorry, so I have to go back. So I have to take account of G1 prime and G2 prime. So here we have G1 prime x, and here we have G2 prime x. Okay. So how should I make this clear? Fy G1 prime. So give me a little bit of time to think about. qx qz fx. So it's always confusing. So, but let's let me go backward this time, so that if I can modify this. So let's try to think about adding these two terms. Okay. So we clear this one. Okay. So then let's think about A, B, G1, G2 of QZ. In this case, I'm going to plug in X, Y, Z coordinates here. So this is X and Y and FXY. Multiply FX, XY. And then plus QX, XY, FXY. And that's it, right? Just this. And dy dx. So that's the adding these two parts. And let's see how can we obtain this kind of formula here. So what's this? So this is equal to what? If I take a partial derivative of q in terms of xy, fxy, right? Then I get this expression. First of all, I get xq by taking partial derivative on the first part, and qy disappears because partial derivative of y by x is 0, and qz appears because I take the partial derivative of the last one here. So this is basically the qx, okay? That's qx. And now, okay, it's qx. Well, since we already cheated a little bit, so why can't we cheat them more? All right, so we have something that we want to integrate, which is qx over the domain D. Okay, let's rewrite that in terms of double integration. So we want to integrate this. Now, I want to re-express my D again. So originally I set my D as this kind of figure, where x is from A to B, and y is from G1 to G2. But in this case, let's express, not sure whether this succeed. So, no, let's not do this way. So I have an idea. So we have qx dx dy. So it kind of looks like we have qx minus 0 dx dy, right? So which means that it sounds like Green's theorem, where p is 0, but q is not this 0. So what if we apply the Green's theorem to this double integration? We can transform that into line integration over this two-dimensional curve. So this is D, and this is curve C. So let's apply Green's theorem here. Okay. Then, so forgive me more about the notation here. So I'm going to call it C bar because C was originally given as a three-dimensional curve. So this is equals to line integration over closed curve C bar of what? Original vector field, but I'm assuming my P is 0. Well, you can call it any constant function, but I just make it a 0 for simplicity. Okay? And let's see what we get when we do this. So basically, I'm going to parameterize the same way we did. So I'm going to parameterize C1 bar and C2 bar. So this is equals to C1 bar integration of Q dy plus C2 bar integration Q dy. So we'll keep saying that there's another way of writing the line integration of a vector field. You can write it as 0 times dx plus q times dy. So that's how I write this, because 0 times dx disappears. You only have dy here. And then let's start to compute. So C1 is parameterized by x, and x-axis range from A to B. And the variable of q follows the points on C1 bar. So it's x, comma g1x. And q is not two-variable function, it's three-variable function. So third variable is defined by f x g1x. Okay? And then, what is dy? Do I have to multiply with dy? So we are following these curves, and this curve is the graph of y equals to g1x. So dy is minus? No, I mean we are moving forward here, so we don't have minus. But dy is not just dx, but we have multiplication of g1 prime x. g1 prime x dx. So that's the first part. How about the second part? Now we are moving backward, kind of backward here, but it's a counterclockwise. So x is from b to a of qx g to x and fx g to x. And then multiply with dy again. But now that dy is different dy from the first one because we are moving along this graph of g2x function. So we need to multiply g2 prime x dx to replace dy here. So if we combine these two, we have to put the same limit here, take minus ab. And what do we get? We get exactly the same on the second part of this line integration, right? So where did it come from? We're taking these two integration. All right? And let's take about talking about the third part. So what we left is these two. And I want to cheat a little bit again. So let's start from here. What we are doing here is just taking a double integration over d of rx xy fxy times fy xy minus ry xy fxy times fx xy dx dy. So let's look at the integrand carefully, and what does it look like? What does it look like? So let's cheat a little bit more. So we finally, I mean, eventually we want this to derive from here. Okay. So there's a common part. It's a kind of common part. Well, let's say this part, like r times fx, is similar. R times fx. And there's also another part, r times y, right? Is the formula correct? If the formula is incorrect, then we are doing nothing here. So I believed you, but just to make sure, I want to check again. So the curl PQR IJK and I part. Okay, so J part. Okay, right, okay. Formula is correct. Okay. What are we doing here? Any thoughts? So it seems like I'm taking over integration, the derivative of x, because I take the partial derivative of x about r. But then I have multiplication of fy, right? So if I had just r, then if I take the partial derivative of x, then this should be just rx, because I have to multiply with 1, and then plus rz times fx, something like this, right? But I have a very weird thing that I have rx times fy, right? What's going on here? Mm-hmm. So let's cheat again a little bit more. So how we derive the second part equal is using the Green theorem, right? So I had a qx, which is simple to consider as qx minus px. I want to do the similar. I want to make this something like qx minus px. Yes, you have any idea?
한국어로 말해도 돼요?
네.
그 상태로 3세되는 거 빼면은 q 편입은 x하고 빼기 p의 y 편입은 하면 바로 그랜시널에 적용할 수 있을 것 같아요.
qx plus qx?
qx 마이너스 qy.
아, something, okay, partial derivative of something minus partial derivative of something. So what should be inside here?
q 전체.
Q? Where's Q? This is about R. I mean, you mean R? well, maybe since we don't know what that is yet, let's put A here, okay, or B here, okay. Then I can use the Green theorem, right? So A dx plus B dy, okay? Well, I'm going backwards to find out what that AB is. If I can find out what AB is to give to give this one, then I'm done. So let's go backward. So this is the same idea that I described here. It's split into two parts, C1 and C2, right? So for C1 part, from A to B of, yeah, I have to put everything here. So, okay, so A, X, G1X, F, X, G1X, and dx. And B, same thing. But then I have to multiply with dy, so I have to multiply g1 prime x dx. That's the C1. And how about C2? We go backward. So instead of g1, we have g2. Actually, I can put dx, 1 dx at the end. And then bx g2x fx g2x times g2 prime, okay? Dx. Okay. So if I change my limits to a to b, I'm minus. And I want this expression to be equal to the last expression here. So what should be my a? R? R?
You're trying to see the equivalence between the last equation
And this one?
and the underlying equation.
Yes. This on the line. What if my a is r times fx and b is r times fy? How about that? Make sense?
Yes, but can you make a clear, the last?
This one? Like there's no room for dx, but yeah, the dx. That makes sense? So if you just plug in x, g on x, and f to x, y, z places for r and fx and r and fy, you get exactly the same formula for the last parts, right? All right, so I found one. And so what I was going to do. So okay, so I just forgot my purpose. So what we are going to do is, all right. Okay, so we had we have formula, and this is set to be the expression of these two, okay? And then we can translate the Green theorem to match with the last part of the Stokes theorem, and we're done.
Right.
That's it, okay?
Because we compare all the components.
Right. So these A, B are just intermediate functions, okay, to connect these two, okay? It's not that they have some special meaning, it's just the intermediate functions, okay. So this gives us very special proof for special situation where you have a surface given as a graph of a two variable functions, and this surface is defined over some convex domain, like D here. But you can, if you have a general shape surface, you can split that into smaller pieces and try to project on XY plane. And if it's impossible, then you can project on the YZ plane or XZ plane to make the same argument that we did here. So you can generalize this proof to apply the general shaped surface. So this is the surface, this is the Stokes theorem, the rigorous proof. Any questions? Yes.
Well, is there, well, we actually, I mean, this is not, I'm sorry to say that this is cheating, but this is not the way that, it is not a recommended way to prove something like, because since we know the result, then we only have to do is just comparing each components of integrals.
Yeah.
From left-hand side to the right-hand side.
Yeah.
So, is there any way that we can use the intuitive understanding of left-hand side and right-hand side so that even we don't know the result, is there any way that we can induce the final result?
So, yeah, I know what your point is. So, the question is, so it seems like it's not an intuitive way to prove because I kind of used the fact that this is equal to kind of match these two formulas together. And the question is there any way to intuitive method to prove this Stokes theorem? So it's a good question because you have to change your paradigm of understanding mathematics because we are accustomed to see the proof that is written from A to Z in a logical sense. But when you really work with mathematics, no one does that. No one does proof like that. Because this is a side note, okay? So to answer your question quickly, if you want the intuitive way to prove, then try to rewrite everything from the beginning. Let's say we start from here, and then try to split these terms, and then just follow what we have done as if we know the answer already here. Okay, let's say A is this and B is this, and we can rewrite this and with this transformed into that, and then you combine everything, that it makes the line integral. Okay, then it's the proof, end of the proof. We show that the surface integral of a curve is same as the line integral of the vector field. And that's the intuitive or smooth way to prove the Stokes theorem. I did kind of back and forth. So here's the result. Here's the assumption. And here's the result, or the conclusion. We know that this assumption leads to the conclusion in this case. So how we approached the proof is somehow using assumption and derives at some level, and then from the conclusion we derive a certain level, and then try to modify each part, and then to see it matches together at some level. Okay. This is how mathematics is done in general. Even though you don't know whether it's true, that we have a conjecture that this assumption may lead to this conclusion with intuitive thinking that it should be true, then how you first prove your conjecture is the same way we just did here. So start from assumption, you generalize or you derive a little bit, and then from conclusion you derive a little bit, and if it met at some places, then you prove the conclusion, and we prove the conjecture. And when you have to write that as a paper or in a document, then you have to kind of go backward to this direction for this part, and then see if, write as if you have done the smooth logical argument from assumption to conclusion. But what happens exactly is that it happened in this way. Okay. And then it happens that you have a contradiction at some point. Then you prove that the conjecture is wrong, right? So mathematics have done this in this way from the beginning.
So then you mean the most ideal way is to start from assumption. Is the most ideal way is following the pure logical, smooth logical path, which starts from assumption to the conclusion. But actually, you mean in practical way or real way that we actually prove the theorem is that we first the intuition have to be preceded before
Right.
the concrete proof, logical based proof.
Exactly.
And then after we gain intuition, then now we start from assumption and conclusion respectively, and then see whether it is converges or not.
Right. Exactly.
So that's the practical or real mathematician.
Right. That's how real mathematics works. So yeah, so I try to follow the practical way of mathematics done, because 이건 그냥 한국말로 할게요. 그러니까 우리가 수학을 공학으로 배우는 분도 있고, 어쨌든 수학을 수학으로 배우는 사람도 있지만은 괴리가 있단 말이에요. 저도 수학을 전공을 했고, 수학을 나중에 대학원 가서 전공을 할 때 학부에서 배웠던 수학이랑 대학원에서 배웠던 수학이랑 크게 괴리가 있어요. 여러분이 나중에 수학을 전공하지 않더라도 괴리가 많이 느껴질 거예요. 왜냐하면 수학에서는 어떤 책을 보든 간에 과정을 이렇게 하면은 결론이 이렇다. 그 과정에서 또 이렇게 결론이 된다. 뭔가 되게 자연스럽게 흘러간단 말이죠. 그거는 이제 많은 사람들이 여러 가지 분야에서 여러 가지 이제 결과들을 이제 그러니까 만들어낸 것들을 깔끔하게 정리하려고 최대한 깔끔하게 정리한 게 그 방향이고, 실제로는 전혀 그렇게 이용이 되지 않거든요. 근데 맞으면 실험이랑 똑같아요. 내가 실험을 하려면은 결과가 이렇게 나올 거라고 예상을 하고 실험을 해야 되잖아요. 그냥 우연히 내가 넣어봤더니 이게 되더라 이런 건 거의 없어요. 내가 목적이 있어서 이 과정을 하다 보니까 100번을 했는데 한 번에 성공되면 되는 거잖아요. 맞으면 실험도. 그러니까 수학은 이제 뭐 그런 100번 했는데 한 번이라도 안 되면 안 되는 거지만, 근데 그런 과정을 똑같이 한다고요. 그러니까 그거를 저는 학부 때 못 배웠어요. 말하자면은 그냥 책에 있는 걸 그대로 이제 보여주는 그렇게 배웠는데, 이제 그러다 보니까 말하자면은 뭔가 문제를 풀려고 할 때 결론을 보고 이렇게 맞춰 나가려는 이런 방향이 아니라 여기서부터 시작을 하려니까 뭘 가정을 해야 되는지도부터 모르는 거죠. 뭐가 결론인지 모르니까. 그러니까 인투이션이 생기기 어렵거든요. 그거를 최대한 이제 빨리 보여주고 싶었고, 그 두 번째는 이런 과정이 사실은 수학이 재밌는 거거든요. 그러니까 내가 보통 이제 경시대 수학 같은 거 보면은 이제 문제를 푸세요 하면은 그것도 답이 있는 거예요. 근데 이제 답을 이제 유도를 하라고 하는 거죠. 근데 이제 거기서도 사실 이제 이렇게 서로 맞춰 나가면서 쭉쭉쭉 유도하는 풀이 보면은 이제 전혀 이 결론에 가는지 안 가는지 모르고 있는데 이렇게 결론하다 보면 결론이 딱 나오잖아요. 사실 그렇게 푸는 게 아니잖아요. 경시대 수학도 결론을 알고 있으니까, 뭘 원하는지 알고 있으니까 이렇게 좁혀 나가면서 이제 그래서 그렇게 된다 이렇게 푸는 거거든요. 그런 과정이 있어야 재밌는 거거든요. 그래서 그걸 보여주고 싶었어요. 사실 그리고 이렇게 해야 기억에 남지. 저도 이제 보통 책에 보면은 이제 뭐 깔끔한 증명이 있을 거예요. 그러니까 제가 그걸 하려면은 그냥 외워야 돼요. 저도 수학도 사실은 내가 뭔가 증명을 그냥 깔끔하게 하고 싶다 그러면 외우는 수밖에 없어요. 근데 외워가지고는 오래 안 가거든요. 그게 직관도 안 생기고. 그러니까 이런 식으로 내가 직접 증명하는 과정을 해봐야 뭐 이게 제가 뭐 한 가지 방법이 아니잖아요. 사실 이건 제가 생각하는 방식대로 한 건데 이런 방식으로 해야 이제 기억에 남거든요. Is any other questions? Yes. 네.
지금 정리가 증명 과정에서 스토스 정리를 매끄러운 다양성이잖아요. 상위분이 잘 정리된 공면이나 벡터 필드에 대해서 증명하고 이렇게 하고 있잖아요. 근데 만약에 매끄럽지 않은 다양성이거나 스토스 정리를 적용할 수 없는 경우가 잘 이해가 되지 않아요. 예를
네.
들어서 그런 다양식들은 그러면 상위분이 정의되지 않은 벡터 필드라고 생각을 할 수 있나요?
벡터 필드는 그러니까 질문이 뭐냐면 안 들릴 수도 있으니까 다시 제가 리프레이즈를 하면 매끄럽지 않은 다양체 위에서 스톡스 정리가 성립이 안 되면 벡터 필드가 편미분이 안 되는 것이냐라는 게 질문인 거죠. 정리를 하면.
매끄럽지 않은 다양식의 공론 중에 벡터 필드의 편미분이 정의되지 않는 포함이 될 수도 있을까요?
매끄럽지 않은 다양체 다시 한번 얘기해 줄래요? 지금 좀 그러니까 다양체가 매끄럽지 않다는 거랑 편미분이 그러니까 벡터 필드의 편미분이 정의되지 않는 거랑 사실 무관한 거거든요.
그래서 그냥 폭발적인 질문은
네.
정리가 적용되지 못하는 경우가
어떤 경우가 있느냐? 일단 스톡스 정리는 벡터 필드가 일단 스무스해야 돼요. 서피스 위에서 스무스해야 돼요. 그러니까 정확히 말하면은 서피스 위에서만 스무스한 게 아니고 서피스를 포함한 점의 근방에서 스무스를 해야 돼요. 그 다음에 우리가 적분을 할 때 되는 경우만 좀 얘기를 할게요. 적분을 할 때 우리가 한 점 정도는 없어도 적분이 되잖아요. 그래서 공면 중에 내가 어떤 라인을 따라서, 그러니까 면적이 0인 이제 그 부분, 예를 들어서 라인도 면적이 0이고 점도 면적이 0이죠. 그 부분은 유한계만 있으면 스톡스 정리를 적용할 수 있어요. 그 부분은 빠지니까. 그리고 마찬가지로 이제 그 우리가 스톡스 정리를 적용하려고 하는 곡면의 바운더리에서도 곡선이 이렇게 꺾이는 부분이 있을 수 있죠. 그게 유한계만 있으면 괜찮아요. 왜냐하면 유한계 점은 빠지니까. 근데 이제 아예 안 된다 그러면은 경로적분이 안 되거나 면적분이 안 되거나 둘 중에 하나겠죠. 면적분이 안 되는 경우는 아까 얘기한 대로 곡선 곡면에 정의된 그 컬 자체가 그러니까 혹은 벡터장 자체가 발산한다든지 뭐 무한대로 발산하는 그런 경우라든지 아니면은 뭐 미분이 불가능해서 그러니까 미분이 불가능한 경우는 이제 기본적으로 이런 거를 저는 생각을 해요. 이렇게 있으면은 이거 아마 응미미 때 보셨을 수도 있어요. 사인 이런 경우는 이제 미분이 안 되죠. 연속이지만. 그럼 벡터장이 뭐 이런 식으로 내가 어떤 한 점에서 막 엄청나게 이제 진동을 한다든지 그런 경우는 이제 안 되는 거죠. 그 경우 말고는 뭐 이게 되게 말하자면 실제 상황에서는 등장하기 어려운 케이스인데 이제 수학적으로는 이렇게 애드호크로 만드는 거 외에는 전 생각하기 어려울 것 같아요.
자연계에서는 대체로 다 가능할 것 같아요.
그렇죠.
연속적인
네네. 네. 그러니까 모델링만 잘 돼 있으면은 사실 뭐 스톡스 정리는 다 적용이 되죠. 발산 정리도 증명은 할 수 있는데 일단 간단하게만 얘기를 하고 사실 이번 시간에는 저거 얘기를 하고 싶었어요. 스톡스 정리랑 발산 정리랑 같은 거다. 그 얘기를 하고 싶었어요. 발산 정리만 직관적으로 얘기를 할게요. So divergence theorem. So it says that if you take the flux over closed surface, is equals to the integration of the divergence of the function. So intuitive idea is the following. Let's talk about the small cube inside the volume. So I'm going to take the dimensions of volumes as delta x, delta y, and delta z. Okay. And let's talk about the flux. So there are directions of vector field. When we talk about the flux over upper part and lower part, and I'm assuming that these cubes are very small, that I almost the value between values of vector field are almost same, but if I change the point from here to here, then it's a little bit different. But anyway, so whenever when I take the upper part and lower part, I want to find out the flux of these directions of vector field. Okay. So my vector field is in this direction, I just want to take this part. So by taking the projection onto this z-axis, right? So the flux over the upper and lower boundary is approximately how much? So we had a vector field f, let's assume that coordinate functions are PQR. So I'm just comparing the value of r on here and there. Okay. So I have R, X, Y, Z, and then minus, and also Z plus delta Z minus R, X, Y, Z, okay? And again, this is only changing the Z coordinates, so we can use the mean value theorem because it's difference between two functions on one coordinate Z. So I can approximate this as the partial derivative of R by Z, so which means that I can take a single variable differentiation of function R and then multiply by delta Z. And how much, the flux. So I'm talking about the flux. So I have to take a multiplication with the area of upper part and lower part, so which is delta X, delta Y. Okay? So times delta X, delta Y. So this is how much the flow is, the vector field flows outward to the upper part and lower part. So the reason I take the negative is that actually in the lower part, the normal direction is this direction, but I want to measure the flow outward, but the vector field actually flows inward, so I take the negative here. And we do the same thing for the right part and left part, and then up, front and back, okay? So right and left is approximately, so we are comparing the Q, so this is X direction and this is Y direction and Z direction. So right and left, we are comparing the Q components. So Y plus delta Y, Z minus Q X, Y, Z. And this is approximately QY, and then multiply with F delta X, delta Z. So the parenthesis part by mean value theorem is almost equals to QY times delta Y. So delta X, delta Z. And front and back similarly gives Px delta X, delta Y, delta Z. So sum of all these fluxes are the flux over this closed surface. Okay? So what do we get is the divergence of vector field Px Qy plus Rz times delta X, delta Y, delta Z. So that's the overall flux over small cube. And if you want to find out the total flux over this small, large volume, you can subdivide that volume into smaller pieces of cube. And if you have two cube side by side, then the flux according to the cube above is this direction, but the flux according to the lower cube is this direction. So it cancels out. So what left is only the flux at the outside of the cube matters, because inside it all cancels out. So when you add all fluxes over all small cubes, then it's the flux over the boundary of this volume. And what does it equal to? Because if you compute all the fluxes of smaller cubes, it's equals to the divergence times the volume. So basically we are taking the divergence, the volume integration over the volume bounded by the surface, closed surface of the divergence of the vector field. So that's the intuitive idea of the divergence theorem. And you can actually do the similar proof how I did in the Stokes theorem. Just try to make a special cases of volume, and you can prove rigorously why the divergence theorem works. But let me finish today's class by mention that the Stokes theorem is actually same as divergence theorem. So I'm going to take a Stokes theorem in general situation, and this content is not for freshman year students, but I'm just telling you anyway, because it's interesting. So let me start from the notion of form. So let's say we denote line integral as the following. So we have f dx plus g dy in the two-dimensional case, okay? Or in the three-dimensional case, we could have write that as one more coordinates here by taking dz part, okay? So meaning that I have a two-dimensional curve, and this is two-dimensional vector field whose coordinate functions are fg, and here we have vector field whose coordinate functions are fgh. Okay? Now, whenever we talk about the integration, this dx, dy, or dz is kind of symbolic expression, meaning that we are taking a one variable function integration. But mathematicians have developed a theory about the forms, and in that sense, this dx, dy is a mathematical object that you can actually work on. So these are called one forms, and these are also one forms. So the reason why we call the same one form is that the one is comes from how many dx are put together here. So here we have one dx, here we have one dy. So the linear combination of these dy's or dx are just gives one form, and adding dz again is still one form. So what is two form? How I increase this number here is that you take a wedge product of two forms, two one forms. So for example, I can take dx wedge dy, and this becomes two form. This is two form. Now, the wedge product has some properties or criterion that if you take the wedge product of the same one form, it's always zero. Okay, and because of this property, we have if we have dx dy as one form and dx dy and wedge with dx plus dy, then the wedge product is also linear function. So I can split that linearly. So I get dx plus dy dx plus dx dy plus dy dx dy dy. So we know that these two goes 0, and we have dy wedge dx plus dx wedge dy equals to 0. Therefore, we can conclude that dx wedge dy is equals to dy dx minus dy dx. Okay, this is the property of wedge. So why does appears, have to explain from beginning about what's the partial derivative, what's the vectors and what's the covector and so on. But let's take that as a theorem, okay? I mean, or just the axiom, so for now. Okay, so one more thing. There is a D operation. And the operator works as follows. So when you have a one form, for example, f dx plus g dy, then you can make, so this is one form. You can make a two form out of one form by taking d operator and call it dw, d omega. And how it works is the following. So you have dx dy with coefficient function fg, and these fg are two variable functions. We are going to take a total differentiation of this f and g. So first of all, fx dx plus fy dy and wedge dx, okay? Plus what? Gx dx plus gy dy wedge dy. So as I said, if you add wedge the same thing here, it disappears. Here it disappears, and we have dy wedge dx, which can be written as minus dx dy wedge. So combined with this, we have gx minus fy dx wedge dy. Now it becomes two form, okay? You can apply that to any n form to make n plus one form. So this is all we need to express the general Stokes theorem. So here's the statement. So we have M as m-dimensional, or let's say n-dimensional, m-dimensional. I want to say a word manifold, but let's not use that m-dimensional space, okay? And put a quote on it, because maybe the word space means is more intuitive than the word manifold. And let's say I will call dm, curly d, m as the boundary of D. And I'm going to call M as closed space. And if I take the boundary of m-dimensional space, it's m minus 1 dimensional, n minus 1 dimensional. Okay. And the Stokes theorem also, okay, so maybe let's take omega as n minus 1 form on this boundary, okay? N minus 1 form. So go back to the original examples here. So if n is 2, my omega is 1 form, so it looks like there. And we're talking about two-dimensional space and one-dimensional boundary of that space. So the theorem tells you that the integration of d omega is equals to integration of omega over the boundary of M. That's the Stokes theorem. So I'm not going to prove this, but I'm going to show you why does it make sense in our context? So let's talk about the Stokes theorems that we have observed in a concrete form. So let's say I want to talk about the line integral over closed line, a closed curve. And let's say I want to take a line integral, P, Q, R. Okay? Or maybe let's talk about the Green theorem first in two-dimensional. Okay? The Stokes theorem in general form tells you that the C is the boundary of some two-dimensional domain. So this is our C. And W, omega, is this thing. Okay, so this is omega, and C is the boundary. And here I can translate to, according to the Stokes theorem here, translate to integration over the region D bounded by C of D of P dx Q dy. And what's this? I take Px dx Qy dy, total differentiation of P, wedge dx, and Qx dx plus Qy dy, dy. And I said this disappears. What happens is, sorry, why do I have Q here? It's P. I have dx wedge dy of Qx and minus Py over D. The Green theorem, right? Let's talk about Stokes theorem. So we are talking about line integration of vector field written in this way. And this Stokes theorem tells you that I can rewrite this into the surface integration of derivative, D operator on this one form. So D of P dx Q dy, sorry, is it Stokes theorem? Yes. So, yes, Q dy plus R dz here. So it doesn't matter whether I put the double S or triple S here. It's just meaning I'm taking integration. So don't worry about the number of S here. Now, what's going on when I take the d of P dx? So I have to take a total differentiation, but let's skip some steps. I don't have Px appears because it will disappear because of dx wedge dx. So simple calculation says that Py dy, Pz dz, wedge dx, and Qx dx, Qz dz, wedge dy, and Rx dx, Ry dy, wedge dz. And let's combine dx dy wedge. Okay, so we have dx dy here. So we have Qx minus Py dx dy. And then let's combine yz. So yz here and yz there. Let's keep the order same. So we have ry minus qz dy dz. And take zx, dz dx here. So we have dz dx wedge order. We have pz minus dz dx rx. dz dx. Okay. Does it look similar to something? So we've transformed our one-form integration into two-form integration over the surface. Now we can give a meaning to that. Okay. So what's the meaning of this part? So it's same as this guy. So here we have dx dy as if it's just the dx dy in double integration. So meaning that we are integrating over xy, a region in xy plane, right? How about this? So we are in a three-dimensional space. Actually, the dimension doesn't matter, but suppose that we are at the three-dimensional space, and we want to compute the integration of these two forms. And we have xy as a range for the variables. There's no z part. Okay, so you can assume that z is fixed. We're only talking about the coordinate x and y. We are taking an integration over xy plane, as if it's on the xy plane, of this scalar function, qx minus py. So you can give a meaning on these two forms that we are taking a flux over the plane on a surface in the which is parallel to xy plane direction of these functions, of this function. So if you're talking about the fluxes in the sense of flux, we want to measure how much of a flux of this scalar function flows out to the direction of normal, to the direction of perpendicular direction to xy plane. So here's, let's say, a surface, and you want to measure. So this is x, and this is y, and this is z. Okay. So if you have a vector field f, there is, you want to measure how much is flowing out to the orthogonal direction of the tangent plane, not the tangent plane, plane parallel to xy plane. And the second part here is that I want the plane parallel to yz plane, right? So let's say put plane here. So it's not a tangent plane anymore. We have a surface, but we're talking about the point on the surface, and then I put the plane parallel to yz plane here, and I want to measure how much is flowing out in that direction. And also the last one is the plane parallel to xz plane, and I want to measure how much is flowing out that direction. If you combine all these three terms, it's actually the flux flowing out from the tangent direction of this surface. Okay, so that's the flux. That's the Stokes theorem. And now, so what's the x direction? In order to have x direction, you need the x direction. The x-axis direction is the normal direction to yz plane, right? So this is the x-coordinate for the vector field that you want to compute as a flux. And how do you get the y-axis, y direction? It is the normal direction to zx plane, right? So this is the second coordinates for the vector field, and this is the third coordinate for the vector field. That's exactly the curl, right? So that's the curl of f, and you take the flux over S. Let's talk about the divergence theorem. Now we have a closed surface. I want to find out the flux. So P is the x direction. So in order to have an x direction, I need an orthogonal x direction or orthogonal to zy axis. So the reason why I put that order, sorry, yz, right? YZ is correct order, right? So, sorry. The ZX is correct. ZX is correct, but yeah, YZ here. Yeah. What am I doing here? So, YZ and Q, and that's the second coordinate of the vector field that we want to compute the flux in y direction. How do you get the y direction? 왔어요?
네, 죄송합니다.
맨날 제 시간에 보내주라고
죄송합니다.
아니 괜찮아. 예. So how do you get the y direction? So you have zx direction, right? So dz, dx. And r is the z direction. You have dx, dy. So that's the flux over the closed surface, for any surface actually. But you know, in the Stokes theorem, S is closed. So it says that, so now this is the del M, okay, the boundary. And inside the volume, which is V, is same as the D of these two form, P dy dz, Q dz dx, R dx dy. Okay, now it's interesting. So the formulation is same. So you have to take the total differentiation on each coordinate functions. And each total differentiation gives either dx, dy, or dz in the summation. But if you have dy or dz, then there's two wedge sum. Or let me carry out the computation. So first of all, we have p dx, py dy, pz dz, wedge dy dz, and so on. So let's look at the first term. We have dx, wedge, dy, dz. All three are different, so it survives. But if I take the wedge between dy, dz, we have dy, wedge, dy becomes 0. It kills. Okay. How about dz, wedge, dy, dz? I can interchange the places of dz and dy. It gives a negative sign. But when I do that, we have dz, wedge, dz again. So it kills. So what left is just the first part, px dx, wedge dy, dz. Okay. How about the second part? If I take the wedge, the total differentiation, I only have dy term survive. Okay. So qy dy wedge dz dx. And then how about r? I only have dz part dx dy. Right? So we have three form, but let's make it same. So we have dx, dy, dz in this order. So let's make the same order here. So let's take my dx to the front part. So I have to switch my dx, dz, and then switch dy, dx. So I have two switches, which means that I have two negative signs. So it becomes positive. So this is equals to qy dx wedge dy dz. How about here? I have to make dz to the last. I have to make two switches, so makes the same sign. So this is equals to rz dx dy wedge dz. So conclusion, I have integration over v of px qi rz of dx dy y dz. Divergence theorem. Okay. Yes.
It seems, well, this is just my observation. When we observe the properties of wedge, the operator wedge, it seems it is very analogous to the cross product. But
Yes.
is there any particular reason why we use wedge instead of using cross product? Is there
Sometimes, so first of all, wedge is the operation between forms. The cross product is about the operation between vectors. So in geometry, vector is considered as the differential operator, del del x or del del y, such as that. And this form is a dual vector to that operator, partial differentiation operator. Dual. So there's a concept of dual vectors when you talk in the linear algebra. So anyway, so yeah, so the wedge product is only for the forms, but you're right. Some contexts use this symbol just as a symbol to represent the cross product. And it's interesting that the cross product is not only defined for three-dimensional vectors, you can also generalize the cross product to n-dimensional vectors. So there's a meaning to that. And yeah, since this is brought up again, so the reason why we have the property that dx wedge dy is equals to minus of dy dx is that whenever you think about the dx dy, we are talking about the plane that is parallel to xy. This plane has an orientation, either upward or downward in three-dimensional space, for example, right? So the order of wedge gives the orientation, okay? And this orientation gives in the integration gives the normal direction to the flux and normal direction to so any integration. So that's important. And this somehow also leads to the argument that if you remember, any space has two orientation. Either it's three-dimensional or four-dimensional, five-dimensional. If you can think about any orientable space that you can give an orientation, you can give only two orientation. That two orientation is related to the fact that if you think about the n form, n form on n-dimensional space, this only can be written in terms of dx1 to dx2 to dxn or minus to that. This is the only way you can write, because the wedge product can be switched each other to get the negative, but if you lay out your dxi's, all different dxi's in any order, you can rearrange by switching each other, and the result is either you get the plus of these or minus of these. So that's why we always have a two orientation. Okay, so this is just a side note, and frankly, this is not for everyone, but I think this might be interesting, even though for someone who not considering math major. So thank you very much for today, and we have a deadline today midnight for all the assignments. So please finish your assignment. And we will have a class to next week, right? And